My name is James. Today I will presenting my final project proposal for the reinforcement learning course. My project is titled Reinforcement Learning for Text to Motion Generation, Learning from Human Feedback with Limited Labeled Data. This project explores how we can use reinforcement learning techniques to generate realistic human motion sequences from natural language descriptions, addressing the critical challenge of data scarcity through preference learning. Here's the outline of my presentation today. I'll begin by introducing the problem background and explaining why this problem is worth pursuing. Then I'll discuss the limitations of prior methods and why reinforcement learning is particularly suitable for this task. After covering related work, I'll present my proposed method, evaluation plan, and expected contributions. Finally, I will walk through the project timeline. Let's begin with the problem background. So what exactly is text-to-motion generation? The goal is simply but challenging. We want to generate realistic human motion sequences directly from natural language description. This technology has numerous practical applications. In animation and film production, it could dramatically reduce the time and cost of creating character animations. Video game developers could use it to generate diverse character movement on the fly. Virtual reality applications could create more immersive experience with natural motion, and if it even has applications in robotics training, where we need to teach robots human-like movement. Let me show you a concrete example on the right. If we input the text "a person walks forward and raises his left arm and finally jumps," the system should output a complete 3D motion sequence showing a skeleton performing exactly these three actions in order. The figure below shows some qualitative comparison examples from existing work. The key challenge is making the process accurate, efficient, and able to handle complex description. Despite recent progress, text-to-motion generation faces three major challenges. First, data scarcity. Creating training data for this task is extremely expensive. It requires specialized motion capture equipment like the kind you see in movie studios, with, with suits covered in reflective markers. Expert annotation is both costly and labor intensive. It takes about 50 to $100 per motion sequence. Even the largest existing dataset, Human ML3D, only has 14,060 text motion pairs, which is tiny compared to dataset in natural language processing or computer vision. Second, complex alignment issue. Even when we have data, models struggle with three specific types of errors, shown here in red. Motion integrity refers to cases where the generating motion is missing if is missing event entirely. For example, if the prompt says walk, wave, and turn, but the model only generates walking and turning, skipping the wave. Temporal order problems occur when all actions are present but in the wrong sequence, and frequency errors happen when the model generates the wrong number of repetitions, like jumping once when the prompt says jump three times. Third, long sequence synthesis. When dealing with complex multi-event descriptions involving three or more actions, maintaining coherence becomes very difficult. The model tend to lose track of what it's supposed to do, especially over longer sequences. These challenges motivate our use of reinforcement learning, as we will see shortly. You might ask, why should we work on this problem? I see three compelling reasons. First, the practical impact. There's enormous demand in entertainment, gaming, and VR industries. The global animation industry is worth over $270 billion as of 2024, and there's a huge bottleneck in context creation. If we can democratize animation creation, meaning allow no expert to create professional quality animations. We could dramatically reduce cost and development time. Beyond entertainment, this technology has application in assistive robotics and human robot interaction. Second, this is a fascinating technical challenge. It's a multimodal learning problem requiring us to bridge natural language understanding with motion generation. We need to understand both temporal dynamics, how actions unfold over time, and spatial relationships, how different body parts coordinate. Data efficiency is critical because, as I mentioned, annotation costs are prohibitive. Third, this represents a valuable research opportunity. Surprisingly, there has been very limited exploration of RL in the text-to-motion domain. Meanwhile, RLHF, reinforcement learning from human feedback has revolutionized language models like ChatGPT and Claude. We also have the opportunity to apply vision language models like GPT-4 Vision in a novel way for reward modeling. All these factors make these an ideal project for exploring practical RL applications. On personal level, why did I choose this topic specifically? First, I wanted to explore practical applications of RL beyond the typical domains we study like Atari games or robotic arm control. Text to motion generation represent a real-world generative AI problem where RL can make a tangible difference. Second, I'm particularly interested in understanding how RL can address data scarcity and alignment problems. These are fundamental challenges in AI that extend beyond just motion generation. Third, I want to learn deeply about reward modeling and preference learning, which are central in modern AI alignment research. From a learning perspective, this project offers several valuable opportunities to help implement and compare multiple RL algorithms, including PPO, DPO, and IPO. Design real-world function using AI feedback from GPT-4 Vision. Work with multimodal data, combining text and motion, and our experiment with data synthesis approaches, including extracting motion from videos. Essentially, this project bridges the theoretical concept that we have learned in the RL course with cutting edge research in generative AI. Before diving into our RL approach, let's understand why traditional methods fall short. The, stand, the standard supervised learning pipeline is straightforward. First, collect large-scale text motion pairs, thousands of examples where you have both the text description and the corresponding motion. Second, train a model with cross-entropy loss, essentially teaching it to predict the motion sequence given text. Third, evaluate held out test set. This approach has four key limitations. First, the data bottleneck. To achieve reasonable performance, you need at least 10,000 labeled pairs at $50 to $100 per motion for annotations. We're looking at 50, 500,000 to $1 million just to create a dataset. This makes it nearly impossible to scale to new domains like Tai Chi or sign language. Second, supervised learning is fundamentally coarse-grained. It learns from entire sequence. Sorry, it learns from entire sequence labels without understanding what specific error it's making. The model gets the same loss whether it generates motions in the wrong order or slightly imperfect timing. There's no explicit signal telling it to pay attention to temporal order versus frequency versus integrity. These limitations motivate us to look for a better approach. Let me continue with two more critical limitations of supervised learning. Third is uh, mode collapse. Model collapse, model trained with supervised learning tend to generate safe, common motions that appear frequently in the training dataset. They avoid generating rare or complex motion sequences even when prompted, because they are penalized equally for all errors during training. These lead to limited diversity in output and poor performance on complex or unusual requests. Fourth, alignment issues persist even in state-of-the-art models. Even the best current system like MotionGPT and NDM show 20 to 40% alignment errors on standard benchmark. These errors become particularly severe on multi-event sequences with three or more actions. The problem is that supervised learning has no mechanism to incorporate fine-grained feedback about specific types of errors. The key insight here, and this is really important, is that supervised learning treats all errors equally, but in reality, some errors are much more critical than others. Missing an entire action is worse than having slightly imperfect timing. Getting actions in the wrong order is worse than small variations in motion style. We need an approach that can make these distinctions. That's where reinforcement learning comes in. This table summarize the gap between what supervised learning provides and what we actually need. Supervised learning requires large-scale labeled pair, but what we need is to learn from comparisons, what are much easier to obtain which are much easier to obtain. Sorry, it provides fixed labels, but we need fine-grained adaptive feedback. It learns from coarse-grained labels, but we need event label precisions. It's limited to the training distribution, but we need to handle out of distribution scenarios, and financially it costs $500,000 to $1 million for a dataset when we need something more cost effective. This gap is exactly what motivates our RL based approach. As we'll see, reinforcement learning with preference learning can address each of these limitations. Now let's discuss why reinforcement learning is particularly well suited for this problem. I see three key characteristics that makes this a perfect fit for RL. First, and most importantly, feedback is easier than generation. Let me let me explain. Sorry. Let me explain what I mean. It's much easier for a human or even an AI to evaluate motion quality than to create label data from scratch. When you show someone two motion sequences and ask which one better matches the description, they can answer in about 5 minutes without any special expertise. But but creating a labeled motion sequence required like 15 minutes or of expert time with motion capture equipment. That's a 10 times speed up in annotation time. And you don't need the domain experts. This is the same insight that made RLHF successful in language models. Comparison is easier than generation. Second, motion generation is inherently sequential decision making. Each frame or motion token depends on previous one. If you are generating a sequence of walking, then waving, then turning, the model needs to decide at each step, should I continue the current action or transition to the next one? This temporal dependency structure is exactly what RL is designed to handle. RL naturally models these as a Markov decision process where the policy learns to generate the next action based on the current state. Third, RL enables fine-grained reward shaping. We can design specific rewards for different aspects of motion quality. One reward for whether all events are present, another for whether they are in the correct order, another for whether repetitions are correct. This addresses the alignment issues directly. In supervised learning, all these errors are mixed together in a single loss. In RL, in reinforcement learning, we can provide targeted feedback. On the right, you can see how we formulate uh, these as an RL problem. The state consists of the current text prompt plus partial motion sequence generated so far. The action is the next motion token or frame to generate. The reward comes from alignment scores provided by GPT-4 Vision or human feedback. And the policy is our text to motion model that we are training. Let me, let me elaborate four specific advantages of using RL for this problem. First, data efficiency. With preference learning, we can learn from comparison data, which is much easier to collect empirically. About 3,500 preference pairs can match the performance of 14,000 labeled sample in supervised learning. And because we can leverage AI feedback from GPT-4 Vision, we can scale this up without additional human annotation cost. Second, exploration versus exploitation. This is a classic RL strength. The agent can explore diverse motion patterns during training, trying out different ways to execute actions. At the same time, it exploits known good alignment that receives high rewards. The entropy regularization in RL algorithm helps avoid mode collapse by encouraging diversity. This is very different from supervised learning, which tend to collapse to the most common patterns in the training data. Third, online adaptation. This is particularly exciting. We can incorporate feedback during deployment, not just during training. The model can fine-tune itself based on user preferences in real time. This is especially valuable for handling out-of-distribution queries. For example, if a user asks for Tai Chi motions that wasn't that wasn't in the training data, we can retrieve reference videos online and use them as feedback to adapt the model on the fly. Fourth, we have proven success in adjacent domains. RLHF revolutionized language model, ChatGPT, and Cloud use the exact approach. The challenge in language are remarkably similar to motion. Both require multimodal alignment between modalities, language to behavior in one case and text to motion in ours. If RLHF works for language, we have strong reasons to believe it will work for motion. Okay, speaking of success in language model, let me provide some concrete evidence. In the language domain, ChatGPT and InstructGPT from OpenAI use PPO with human preferences and achieve significantly improved alignment and better instruction following. The key insight they validated was that comparison feedback is indeed easier than absolute rating. Instead of asking humans to write perfect responses, they just ask humans to compare responses and then say which is better. This success has translated to the text to motion domain. Instruct Motion in 2024 was the first work to apply RLHF here and show 15% R precision improvement. ATOM in 2025 used GPT-4 Vision as a reward model and achieved a 30% reduction in alignment error. The recently published Motion R1 combined chain of thought reasoning with RL and showed 20% better temporal accuracy. The quantitative evidence is compelling. These aren't marginal improvement. We are talking about 15 to 30% better performance on key metrics. The key takeaway here, and this is really important, if RLHF works for language, which uses discrete tokens, it should work even better for motion, which is continuous and temporal. The continuous nature of motion actually gives us a more flexibility in reward design and optimization. Okay, now let's look at the related work in details. The first key paper is ATOM from CVPR 2025. ATOM made main contributions. First, they created the motion preferred dataset with 5,300 prompts and 80,000 motion pairs. This is the largest preference dataset for text to motion. Second, they introduced event level alignment, explicitly evaluating integrity, temporal order, and frequency separately. Third, they use GPT-4 vision for automated preference annotation, eliminating the need for expensive human labelers. Fourth, they use IPO, identity preference optimization, for fine-tuning, which is a variant of DPO with better theoretical properties. The results were impressive. They achieved a 30% reduction in alignment errors compared to the baseline, better R precision and FID scores, and successfully demonstrated that AI-based reward modeling works. The figure shows their three-stage pipeline, which we will adapt in our work. However, ATOM has three limitations we can address. First, it was only tested on the human ML3D domain with everyday motions. Second, it has no online adaptation mechanism for new motion types. Third, it only compared one RL algorithm, IPO, without exploring alternatives like PPO or DPO. Our project will build on ATOM strengths while addressing these limitations. The second key paper is Instruct Motion from the CVPR 2024 workshop. Instruct Motion was pioneering as the first work to apply RLHF to text-to-motion. They collected 3,500 human preference pairs and compared traditional RLHF using PPO against DPO. They identified a critical issue, reward overfitting, where the model exploits weakness in the reward model. The key finding was that DPO actually outperforms traditional RLHF in a low data region, showing a 15% improvement in R precision. However, Instruct Motion has several limitations we can improve upon. The dataset is relatively small at only 3,500 pairs. The evaluation was coarse-grained without event level analysis, and it relied solely on expensive human annotation rather than AI feedback. Our improvements will be substantial. We will use GPT-4 Vision to scale the data collection. We will implement event-level reward design to provide fine-grained feedback. We will test on out-of-distribution domain like Tai Chi. And it will systematically compare 3 to 4 different RL algorithms to understand their trade-offs. Finally, the third key paper is Motion R1 published in 2022-25. Motion R1 introduced an innovative approach combining chain of thought reasoning with reinforcement learning. Their method works in two stages. First, the reasoning stage decomposes the text prompt into sub-actions. For example, walk, wave, and turn becomes three explicit sub-goals. Second, the generation stage uses RL-guided synthesis to execute each sub-action in sequence. They use motion-specific reward functions and introduce GRPO, Group Relative Policy Optimization, which is a variant of PPO designed for grouped sequences. The key insights from this work are significant. Explicit reasoning improves temporal alignment by 20% on complex multi-event sequences, and the generation process becomes more interpretable because we can see exactly which sub-action is being generated at each step. This is highly relevant to our project for two reasons. First, it validates that RL is particularly effective for complex sequences with multiple action. Second, it shows the importance of decomposition, breaking complex prompts into simpler sub-goals. We might adopt GRPO as a fourth algorithm to compare alongside PPO, DPO, and IPO. This table summarizes and compares all three related works with our planned approach. Instruct Motion used human annotators, collected 3,500 pairs, tested PPO and DPO but had no event level evaluation. ATOM used GPT-4 vision, collected an impressive 18,000 pairs. Used IPO and did include event level evaluation. Motion R1 used mixed annotation methods, focused on GRPO algorithm, and evaluated using chain of thought decomposition. Our planned approach combines the best of all three, where we will use both GPT-4 vision and video-based feedback for annotation. We will target 20,000 to 40,000 preference pairs, substantial but achievable. Critically, we will compare all four RL algorithms: PPO, IPO, DPO, and possibly GRPO, and the ads will include event level evaluation. Our unique contributions are fourfold. First, a systematic algorithm comparison that hasn't been done before. Second, hybrid rewards combining GPT-4 vision with video-based feedback. Third, testing on out-of-distribution domains like Tai Chi and dance that weren't in the traditional data. Fourth, online adaptation capability, allowing real-time fine-tuning from video references. This combination of contribution makes our project distinct from all prior work. Now let me present our proposed method. Um, we will follow a three-stage pipeline adapted from ATOM but with important extensions. Stage 1 is data collection and synthesis. We will generate diverse text prompts ranging from simple single action description to complex multi-event sequences. For each prompt, we will produce multi-motion candidates using the base model, and optionally, this is a stretch goal. We will extract motion from videos for specialized domain like Tai Chi. Stage 2 is reward model design. We will use GPT-4 for vision to score the alignment between between text and motion. The key innovation here is event level evaluation, which separately assesses integrity, temporal, order, and frequency from these scores, and we will collect preference pairs for RL training. Stage 3 is RL fine-tuning. We will fine-tune the base model using our preference data. We'll experiment with multi RL algorithm, PPO, IPO, DPO, and possibly GRPO to understand their trade-off. Finally, we'll evaluate everything on a held-out test set. The figure shows how these stages connect together in the overall pipeline. Let me now go into detail on each stage. Let's start with stage 1, data collection. We will use two complementary approaches. Approach 1 is model-generated data. We will start with Motion GPT, which is pre-trained on human ML3D. For each prompt, we will generate 6 to 10 motion candidates by varying the temperature parameter from 0.8 to 2. Higher temperature give more diversity. Our target is 3,000 to 5,000 prompts, which will give us 20,000 to 40,000 motion sequences. Approach 2 is video-based data for out-of-distribution motions. This is our stretch goal, but potentially very impactful. Impactful. We will target specialized domains like Tai Chi, martial art, and traditional dance that aren't well represented in standard dataset. We'll extract motion from online videos using pose estimation, specifically open pose for 2D key points, then 3D reconstruction. These will be used as reward signals for specialized motions. The innovation block at the bottom highlights a key feature for out-of-distribution queries like Tai Chi. We will retrieve video references online and use them as feedback for online adaptation. This allows our system to handle motion types it has never seen during training. Okay. Stage 2 is where we design our reward model using GPT-4 vision. The process has three steps. First, we render motion sequences to video. We convert the 3D skeleton to actual frames showing the motion. To save on API cost, we sample frames, typically every 8 frames, rather than sending every single frame. Second, we design task-specific prompts for GPT-4 Vision. For integrity, we use a binary score. Either all events are present, score 5, or something is missing, scores 0. For temporal order, we use a 5-point scale from correct order to all motions missing. For frequency, we use a 3-point scale checking if the repetition count matches the, the prompt. Third, we scale all candidates. We batch API calls for efficiency. Then we create preference pairs. A pair consists of motion dot winner and motion L loser, where the score of W is greater than the score of L. The example prompt on the right shows how this works. For a text, a person walks forward, waves arm, turns left. We ask GPT-4 Vision to evaluate temporal order using the 5-point scale shown. At the bottom note, the cost estimation is only 1 cent per motion scoring. For 40,000 motions, that's just $400 compared to $2,000 for human annotation. That's 5 cost reduction makes the approach highly scalable. Stage 3 is RL fine-tuning, where we will compare 4 different approaches. First is PPO, Proximal Policy Optimization. This is the traditional RLHF approach. We train a separate reward model on the preference data, then use PPO to optimize the policy against that reward model. The risk here is reward overfitting and training instability, as instruct motion found. Second is DPO, Direct Preference Optimization. This is simpler. There's no separate reward model. Instead, we directly optimize preference pairs using a supervised learning approach. It's more stable and less prone to reward hacking, where the model exploits weakness in the reward model. Third is IPO, Identity Preference Optimization. This is ADON's choice, and it's variant of DPO with better theoretical properties. The loss function is shown. We minimize the square difference between the preference margin and a target value of 1 over 2 beta. IPO has been shown to work particularly well in the text-to-motion domain. Fourth is GRPO, Group Relative Policy Optimization. This is optional depending on the time, but it is inspired by Motion R1. It does group-based optimization, which is especially good for complex sequences with multiple distinct actions. By comparing all 4 algorithms systematically, we will understand their trade-offs in terms of performance. Let me share the technical implementation details for model architecture. We will use Motion GPT as the base, which has a GPT-2 backbone. We will use LoRa, low-rank adaptation for efficient fine-tuning with rank 8 or 16. This reduces the number of trainable parameters by 90%. The maximum sequence length is 196 frames, and we'll use a VQVA emotion tokenizer with 512 codebooks. For the training setup, we will use PyTorch plus Hugging Face libraries. We will need 1 to 2 GPUs, ideally RTX 3090 or 4090 or better. Each experiment should take 6 to 12 hours, while planning 12 to 15 total experiment rounds to cover different algorithms and hyperparameters. On hyperparameters, we will search over learning rate from 110 learning rate from this range, and batch size will be 32 or 64 preference pairs. The KL penalty beta ranges from 0.01 to 0.1. Lower rank will be either 8 or 16, and we will train for 3 to 5 epochs. For data split, we will use standard 80-10-10-10 for training validation test. That means 16,000 to 32,000 pairs for training, 2,000 to 4,000 for validation and testing. These specifications are all feasible given the compute resources available. Now let me describe our most novel contribution video-based feedback for out-of-distribution motions. Imagine the scenario: a user inputs a person performing Tai Chi, but our model was trained on human ML3D, which contains everyday motions like walking, jumping, and waving, no Tai Chi at all. What do we do? Our solution has 4 steps. Step 1: detect the OOD query. We check if Tai Chi appears anywhere in our training dataset. If, if it doesn't, so we trigger the video retrieval module. Step 2: retrieve video reference. We search YouTube or a cache database for Tai Chi videos. We select the top 3 to 5 representative clips and extract motion sequences using pose estimation. Step 3: compute video-based reward. We generate 5 to 10 candidate motion from our model. We compare each candidate with a video reference using either L2 distance in the motion space or feature similarity from a pre-trained encoder. Additionally, we can use GPT-4 Vision to score them by asking which motion looks more like Tai Chi. Step 4: optional online fine-tuning. We create preferences pairs from the scored candidate, those that matches the video better versus those that match worst. Then we do a quick RL update with just 5 to 10 gradient steps. This improves the model future generations when users ask for Tai Chi again. This entire process happens online, potentially in real time. It allows our system to handle motion domains it has never been trained on, which is a significant advantage over pure supervised approaches. For evaluation, we need strong baseline to compare against. First is MotionGPT. The base model is pre-trained on human ML3D with 14,600 pairs, but it has no preference fine-tuning. This represents the starting point and tells us how much improvement RL provides. Second is supervised fine-tuning, or SFT. We take only the highest score motion from our generated data and fine-tune with standard supervised learning, no RL involved. This baseline tests whether the improvement comes from RL specifically or just from better data selection. Third is instruct motion. If we can reproduce it, it uses human preference-based RLHF and represent the published um, baseline we can compare against. We may need to request code or data from the output. Fourth is ATOM if the dataset is available. This use GPT-4 Vision plus IPO and will represent the current state of the art. For alignment, it would be our gold standard for event level evaluation. By comparing against all 4 baseline, we can isolate the contribution of different components, the algorithm choice, the reward design, and the data collection strategy. We will evaluate our approach using 3 categories of metrics. First, standard metrics used throughout the text-to-motion literature are precision, measure retrieval accuracy. Given a motion, can we retrieve the correct text description from a set of candidates? We'll report top 1, top 2, and top 3. Higher is better. FID, fresher, inception distance, measure motion quality and realism by comparing feature distribution. Lower is better. Diversity measures the variance in generating motion across different prompts. Higher means more diverse output. Multimodality measures diversity for the same prompt. Can the model generate different valid interpretation? Again, higher is better. Second is task-specific event level metrics that directly measure alignment. Integrity score is the percentage of generated motion that contain all events mentioned in the prompt. Temporal accuracy is the percentage with correct event order. Frequency accuracy is the percentage with correct repetition count. These three metrics directly correspond to the three alignment issues we identified at the beginning. Third, optional human evaluation for validation. We will do side-by-side comparisons where human choice between our method and baseline. We'll use a 5-point Likert scale rating realism, alignment, and naturalness. We will evaluate 50 to 100 test samples, which is enough for statistical significance. Together, these metrics give us a comprehensive picture of performance from multiple agents. Our test set will have two components. First, in distribution evaluation on human ML3D, we will use 2000 prompts from the standard test split. These are divided into simple prompts with one action, medium with 2 to 3 actions, and complex with 4 or more actions. This let us see how performance scales with prompt complexity. Second, out of distribution OOD, we will create 100 to 200 prompts for domains not in human ML3D. For Tai Chi, we will have 50 prompts like perform cloud hands or do the opening movement or traditional dance, another 50 prompts, and if time permits, 50 prompts for sign language. Our evaluation will focus on three priorities. Primary focus is event level alignment, the integrity, temporal, and frequency metrics. These directly measure whether we have solved the core problem. Secondary focus is standard metrics like R precision and FID to ensure we haven't sacrificed overall quality. Tertiary focus is OOD generalization on Tai Chi and dance to validate our video-based feedback approach. This protocol ensures we thoroughly test both the main contribution and the novel OOD handling capabilities. Let me summarize our expected contribution in three categories. First, technical contribution. We will provide a systematic algorithm comparison starting PPO versus DPO versus IPO and possibly GRPO for text-to-motion. No prior work has done this comprehensive comparison. We will demonstrate hybrid reward design that combines GPT-4 vision with video-based feedback. We will show a novel OOD adaptation approach for handling unseen motion domains and will release a dataset of 20 to 40 preference pairs with event-level annotations. Second, empirical findings. We will quantify the trade-off between RL algorithm in terms of sample efficiency, training stability, and final performance. We will measure the impact of fine-grained event-level rewards versus coarse-grained rewards. We will evaluate the cost-effectiveness of GPT-4 vision versus human annotation, both in terms of money and annotation quality, and will demonstrate that online adaptation works for OOD domains. Third, practical impact. We will open source our code and dataset for full reproducibility. We will provide guidelines for applying RLHF to all generative motion tasks beyond text to motion, and there's potential for deployment in actual animation and gaming pipeline, though that's beyond the scope of this academic project. These contributions span theory, empirics, and practice, making these a well-rounded project, I think. Okay. From learning perspective, this project connects directly to RL Crow's concept in four ways. First, policy optimization. We will implement PPO from scratch or using the TRL library. We will deeply understand KL divergence constraint and why they are necessary. And we will compare on-policy algorithms like PPO with off-policy style approaches like DPO and IPO. Second, reward design. We will design multi-objective reward balancing integrity, temporal order, and frequency. We will implement the exploitation trade-off through temperature and entropy regularization, and we will work with both sparse and dense rewards, understanding which when each is appropriate. Third, preference learning. We will understand the Bradley-Terry model that underlines most preference learning approaches. We will implement the TPO laws shown here, which directly optimize preference probabilities, and we will compare it with the IPO variant that squares the margin. Fourth, multimodal RL, we will handle both text and motion modalities simultaneously. We will solve temporal credit assignment problems, determine which action at which time step deserve credit for the final reward, and we will work with sequential decision making, where each decision affects future options. These learning outcomes ensure the project is pedagogically valuable, not just a research contribution. And here's our proposed timeline with clear milestones. Okay. So, um, in summary, uh, we may conclude with a summary of why this project matters. The problem text to motion generation suffers from data scarcity. Annotation costs $50 to $100 per sample, and alignment issues include integrity, temporal order, and frequency errors. Why RL? Three reasons. Feedback through comparison is 10 times faster than creating labels. Fine grained rewarding, shaping enable level alignment that supervised learning can provide, and we have proven success in language model through RLHF, suggesting this approach will transfer to motion. Our approach a three-stage pipeline: first, data synthesis, generating diverse prompts and motion candidates; second, GPT-4 vision reward model providing event-level scores; third, RL fine-tuning comparison, PPO, DPO, IPO, and potentially GRPO. Our novel contribution is video-based feedback, enabling adaptation to OOD domains like Tai Chi. Expected impact: we anticipate 15 maybe to 30% improvement in alignment metrics. Based on prior work, we will achieve cost-effective scaling through AI feedback rather than expensive human annotation, and we will demonstrate generalization to unseen motion domains, which no prior work has shown. This project bridges reinforcement learning theory with practical generative AI, addresses real limitation in current methods, and provides both technical and empirical contribution to the field. Thank you for your attention. I'm happy to take any question.